So here we are again in one of our R Markdown files, and let's take a look at what we already have in. So first we loaded in the library reg class. This is very important so you can use the data sets inside of it. Next we loaded up the data set survey 10, which is inside of reg class. You have to have reg class on to load this. You notice survey 10 is over here now. Next we have the names that we want to look at. This is all the column heads inside of survey 10. So this tells us the variable names. Next, we are going to run an associate command. The associate command is y tilde x, and then we do data equals because we're using stuff inside of a data frame. So these are variables inside of a data frame. They're not just hanging out here out in the open, and we would see that if we saw something like, if we had x, let's do equals, and I'm just making something hanging out here in the open. You see it's under values. So that would be there. You do not need to do that. That just shows it's hanging out there. And I'm going to remove also the make exam. Just remove both those things and keep my data frame or everything nice and clean over there. So that just shows you the difference between having a value over there or having something in a data frame which has the values or the vectors inside of it. So that's why we have to do the data equals because it's not just floating out here. So when we go ahead and run this, let's go ahead and analyze the output right here. We have it running. We're going to get these permutation plots in just a moment here. And here we are. Now I'm going to knit this to HTML. Please do not turn in your documents via HTML. So it's going to be nice and easy and open up a simple browser right here with the knitted document. And we'll get to see everything we have. So let's take a look at it here. 3, 2, 1. There we go. So here we are and looking at our analysis. So let's take a look at the graphics first. We'll get down to the data in a second. We have right here the min value, we have the Q1 value, the median, the Q3, and the max for females. It's important to note that the min is the lowest point and the Q1 and Q3 are the box of the box plot. You'll also notice the mean right here indicating a left skew. We'll talk more about that in a moment. Then we have the male box plot. We have the lowest GPA for males. We have the Q1 and the Q3 and the mean right there. We also have the max right here. So this is just side-by-side box plots analyzing GPA by gender. Gender is the X variable and GPA is the Y variable. Next we have side-by-side histograms, and these side-by-side histograms are analyzing GPA, but one for male, one for female. So we have the male and the female side-by-side right here. So we get a little better view of the left skew here. They're kind of stacked on the right a little bit, but this is a left skew, and there are outliers on the low side, as in this point right here. Actually, there seems to be 2 or 3 points right there because the bin is a little bit higher. However high this bin is how many observations there are. You see, this is kind of one of our lowest bins, which probably represents this point right in here. So yeah, that's 1.8 or so, and this would be in the 1.8. So everything, these are bin lengths of 0.5 because it goes from 1 to 1.5. And if it was 1.5, it would then go in this bin. 2 would go into this bin, 2.5 in this next bin, and 3 into this next bin. Same thing going on with the males, nothing special here. Left skew, outliers on the low side, and we have a gap. So next we have the normal quantile plots. And the reason I did it this way is because when it knits, it usually looks as best as it's going to look. And we can actually see the whole normal quantile plot here. So the normal quantile plot is still a univariate analysis. It tells you how good the histogram looks on a normal. And the answer is, down here it looks the worst. Up here it looks kind of bad too because it's not going with this line going like that. So we have problems at the high end and we have problems at the low end, because look at this. Do you see this in here? That almost looks like the start of a normal curve, and that's why in here we're seeing it. We're seeing what looks to be a normal curve in this central bulk right here. So this does seem to have a good bit of problems. I do not like this tail with the extreme outliers. I do not like the too many values on the high end right here. This is problematic. I would say this breaks from the normal and is not normal. And the same analysis would be over here. This tells you nothing about curvature because all we're doing is looking at a univariate analysis for does this look normal. The normal quantile plot, known as a normal probability plot or a QQ plot, all names mean the same thing. To review, normal quantile plot, normal probability plot, and QQ plot all mean the same thing. And I can't ever tell you what later on you'll hear in another class or in literature, but they all mean the same thing. It's just, is this a good representation of a normal? And the closer it is to this straight line, the better this histogram will look. It's connected to these. Usually you see the two in tandem. And this looks kind of bad, so this looks kind of bad. So it looks like we have problems with normality. And that's key because we're actually going to make a decision down here on which of these simulations to use. Now, we are randomly assigning people to the group male or female, and we don't care what their GPA is. So we're actually putting people together at random. One of the key things about a p-value is what's the probability of our results or results more extreme happening due to random chance. And in this instance, we're saying if they were put together randomly, we'd probably see no difference. That's why 0 is often down here, because we'd see no discrepancy between males and females if they were put into random groups and their GPA was just what it is. We take 100 people, put them 50 in one group, 50 in another. Why would one group have a higher GPA if we do it randomly? That's the idea of these permutations. We just keep doing that. And what we often see is basically no difference. By random chance, we could get some differences, but it's unlikely that this discrepancy or differences we see would be very large. So now we have to look at our results. Our results are the red lines, and these are different tests right here. When we compare the averages, we're comparing the means. So we're looking at the differences between the means. When we do mean ranks, which we won't do in this class, mean ranks would be to take the rank of every observation and then take the average rank. And this is kind of a good way to downweight outliers, because if you had 100 observations, the one with the highest, the 100th observation, the highest GPA, would still just be 100 if it was a 5.0 or a 6.0 or a 7.0, something ridiculous. If someone was to skew our distribution in that direction, it would downweight it. They would still just be the 100th. They would be the highest, no matter how high they are. You oftentimes see that a lot of times with data sets dealing with like salaries or stuff, if you put the CEO in and they're making $2.5 million, well, if the second highest person is making $100,000, it doesn't matter how high the CEO is if we're doing something that downweights outliers, because then it doesn't matter if they're $101,000 or if they're 2.5 or 2.5 billion. Doesn't matter how big they are because they're still the biggest observation. So that's a good way to downweight outliers. But for us, and for this, since they're not normal, we will take out the impact of the outliers by using the medians. Medians is just using the middle number, which once again, it doesn't matter if the boss is making 100,000 or 2.5 million, because if we use the middle number, the highest number does not change that no matter how high it is. So this downweights outliers and is when we need to use it here, especially when it is skewed. This is a very good idea to use it when it is skewed. We want to use averages when it is normal. And if it's not normal, we have an indication of non-normality, we should use medians. So let's go to the output. We have sample size for males and females. Nothing too special going on right here. Just 313 males were sampled, 386 females were sampled. Now we get to the actual numbers. And using the actual numbers, we see the averages for males, the averages for females, the mean ranks done by a Kruskal-Wallis test, and the medians. And you'll notice there's a pretty big difference among all of them. And the discrepancy is calculated different for each one, but with this in mind, all of these discrepancies are unlikely to have happened by random chance. So especially we need to look at the median output because we're saying it's not normal, so we're going to go with medians. And our result, our difference between medians with this standardized discrepancy value, is unlikely to have happened by random chance. Furthermore, we need to look at the confidence interval for our test. And the confidence interval suggests that we are very certain that it is unlikely to have happened by random chance. Our test is conclusive because our p-value is between 0 and 0.007. So we are definitely conclusive with the results right here. So nice and easy. Let's run a different one here and see if we can get some more interesting results. Let's run the names command again. Let's see who's actually more likely to date people right here. So let's go ahead and run %dateable and put that in the y variable because we want to do categorical x's and we want to do quantitative y's. So let's see if there's a difference between males and females and the % they find more dateable at UT. And whoa, just seeing those red lines right there, there's definitely a difference. So we're going to go ahead and knit this so we can get a little bit of a better view on it and see what's going on in this output. So here we are with our knitted document. And let's scroll up a little bit. Looks like, and this is the % of people who the males or female find dateable. And neither of these are following a normal. This is the way I first kind of analyze it as I look at the QQ plots, especially the bend down here. You see it's very right skew. But the difference is going to be noted because there is a big difference. Here's the plots. And this is how I kind of quickly analyze them. I'm going to use medians because of the right skew, as denoted by the histogram, and the non-normality in the QQ plot. And you'll see that the males, especially right here, you can tell, since the medians are what we're going to compare, the males have the higher median. And the p-value for this is 0.02. Our confidence interval is conclusive. And this can actually, I like this result because I'm going to cheat. And I'm going to use permutations. And I'm going to put them down to 100, which is not generally what you want to do, because generally more permutations are better. But this is going to create non-conclusive results, or most likely will. Cross your fingers. And yes, it did create non-conclusive results. My interval now contains 0.05. So you can't just pick which test you're going to use. You need to go down through the output. You need to look at your histograms and say, these have a right skew. They don't look normal because they have a right skew, so they don't look normal. And that means I'm using medians. Well, it looks like my p-value is kind of low because there's not many results above it. And when we get down here, there was actually only 2 results above it, 1, 2 out of 100. That's 2. The probability of results as extreme or more extreme than ours was 2 out of 100. And then when we go down to the confidence interval, this is where we get into it's inconclusive because our confidence interval contains 0. And what do? We increase the permutations since it's in the range. And you could increase it and you'd find out we have conclusive evidence that males generally, on average, when comparing medians, find more of UT datable than females. And that would be a conclusion I would draw from this. Is that usable? Does that have practical significance? I guess maybe if you're going to run a dating game at UT, you'd say, well, let's get the males because they're open to dating people. I don't know what you'd want to use this for, but there seems to be a small difference between the medians of males the median male for percent datable is 25%. The median for females is 20%. But males are a little bit more open to dating than females are. So there you go. There are the results, and good luck, and email me if you have questions.